Hello again, everybody. I'm sure we're all familiar with this slide by now. So this slide, of course, covers the two main groups of sedimentary rocks that we have. There are, of course, the clastic sedimentary rocks and the non-clastic sedimentary rocks. So the clastic sedimentary rocks are made up of clasts. So a clast is a piece of rock or mineral which is produced by the weathering of a pre-existing rock. Now these clasts range in size. They can go from very, very small sizes like clays and silts all the way up to very, very large sizes like cobbles and boulders. So if you remember, the size of clast being transported is dependent on the energy of the system. So for instance, the more energetic your river is, the larger the clast it can transport. The slower and less energetic your river is, the smaller the clast it can support. So the type of clast that you get in the sediment deposited by a river or a desert, etc., is completely dependent on how much energy the transporting medium has. In the case of the non-clastic sedimentary rocks, typically their formation is dependent on environmental factors. In most cases, the rock that forms typically forms in its location. There's no sediment being transported around over huge distances. Typically, when you form something like coal or an evaporite rock, then where you find it is the location where it formed. It wasn't sourced from anywhere else, it formed exactly right there. So if you remember, non-clastic rocks are essentially of two varieties. There are the organic and inorganic non-clastic rocks. So a good example of an organic non-clastic rock is, of course, coal. Coal is made from undecomposed organic material, so obviously very organic in origin. And an inorganic non-clastic rock would be something like an evaporite rock, so gypsum or halite. And in that situation, we have a body of water evaporating away. As the water goes into the atmosphere, it can't take the dissolved minerals in the water with it, and so the minerals get left behind and they form evaporite rocks. So, as you can tell, non-clastic rocks, once again, dependent on environmental factors to control where and when they form. So, just thinking about clastic rocks for a second, the transport of clast is dependent on the energy of the medium transporting them. So we've already touched on this several times, but clasts can be transported by ice, water, wind, and gravity. So the more powerful the flow, the more energy the transporting medium has, the larger and denser the clasts that can be moved. So as we've already touched on, glaciers can move huge clasts. In contrast, a slow-flowing river can only move relatively small material. So this is obviously reflected in the sediment that's produced in those environments of deposition. A glacier can produce a sediment that's got huge clasts in it. In contrast, a slow-flowing river like a bayou will typically produce sediments which are dominated by muds, clays and silts, and very, very fine sands. Now, we've already touched on the fact that as a clastic sediment is transported, the clasts within that sediment will be eroded physically, and over time the clasts will become better, more rounded, better sorted, and smaller. There is one more change that will also take place though, and that's a chemical change in the sediment. So the longer the sediment is transported for, the more and more time essentially chemically reactive minerals have to be lost. So a chemically reactive mineral is typically a mineral that will often react with water. So a good examples of chemically reactive minerals are minerals like biotite and olivine. Now, both of those minerals don't really like being in contact with water, so if they're being transported as part of a sediment that's in a river, obviously over time the olivine and the biotite will break down and they will be lost from the sediment completely. Typically they'll break down to form clay minerals. And so that means that over time, more reactive minerals are lost and the more stable minerals are retained. In terms of mineral stability, there's essentially three minerals which are considered to be extremely stable in a standard sedimentary system. They are quartz, feldspar, and clay. And if given enough time, even feldspar will break down, leaving just quartz behind. So we can also look at the minerals in our rock to also gauge how long a sediment's been transported for. The longer the period of transportation, the less likely that sediment is to have reactive minerals like biotite and olivine contained within it. Okay, so here's a nice diagram covering just a few of the environments of deposition we're going to touch on today. So if we just have a look at this diagram, though, you can see that depending on the environment, the class size is varying. So for instance, up here, you can see we have glaciers. Well, the glacier is a very, very powerful system. It can move everything from clay-sized particles all the way up to very, very large boulder-sized particles. So when we see a glacial sediment, we would expect to see a very, very poorly sorted sediment. In contrast, something like a lake sediment, well, lakes are extremely low energy environments, so we would expect to see only the finest clastic particles associated with lakes. So lake deposits are typically dominated by silt and clay. Steep mountain deposits, well, once again, those are typically produced by landslides. And so we would expect to find, it's quite an energetic system. So we would expect to find everything ranging from clay-sized particles all the way up to boulders in those kind of systems. A sand, on the other hand, so sand dunes or beach sediments, well, they're typically moderate energy systems. So we would expect to find class sizes ranging from low energy class, like silt and clay, up to the moderate energy class, which would be the sands. We would not, however, expect to find things like boulders, gravels and cobbles, because they would be too large to be moved by the system, and so they would never be in that location in the first place. So you can see that depending on the environment of deposition, we're going to get a very specific class size or class sizes. And that's another piece of evidence that we will use when we try and work out what environment of deposition a rock formed in. Okay, so this diagram here is the Hjulström diagram, and it deals with the transportation of clastic rocks. Now, to be clear, the Hjulström diagram is a lab diagram, so it's not 100% representative of the real world. However, it does give us a very good idea of the kinds of velocities required to move clasts of certain sizes. So if we look at the diagram itself, what can we see? Well, we have clay, silt, sand, gravel, pebbles, cobbles and boulders at the bottom here. So we have class sizes increasing as we move to the right. Please note the class sizes are in millimeters. On this axis here, we have the flow velocity in centimeters per second. So we go from 0.1, 1, 10, 100, 1000. So obviously the flow velocity is increasing as we go up. So obviously, as we've discussed, the higher the velocity, so the more energy your system has, the larger the size of particle that it can transport. So when we have very, very high energy systems, so let's say we have a very, very high energy, like let's just say 1000 centimeters per second. That's a very, very powerful flow. Well, if we come across here, we can see that we are eroding clays, silts, sands, gravels, pebbles, cobbles and boulders. So that means our medium, probably water, is able to essentially extract these particle sizes, these class sizes, and begin to transport them along. So your river is actively eroding. It's breaking down material and transporting that material away. So what you'll notice, though, is that in order to transport something that's a pebble, a cobble or a boulder, let's just say 100 millimeters, a very, very coarse material, you'll notice that you require very, very high energies. There's only a very, very limited period of time, well, flow velocity within which you can actually transport that material. And then once you drop below about 200 centimeters per second, you have to drop that material. It's just too big and too heavy. So this diagram essentially is giving us a view into the kinds of velocities required to erode a particle, so pick it up, to transport a particle, just to either move it along by pushing or by pulling, and depositing the particle, dropping it. So if we were concerned about, let's say, a sand, so let's go for 1 millimeter because it's it's nicely picked out here in red for us. What we can see is in order for a moving body of water to pick up, essentially erode a sand, it has to be moving at speeds of probably about, difficult to say, about 20 centimeters a second. If you're moving at a velocity above 20 centimeters a second, your river has the capacity to physically erode, so take that sand from a sediment and begin transporting it. So it's physically able to lift it away and carry it off. Now, once we drop below 20 centimeters a second, your moving body of water can no longer erode. All it can do is transport the sand that it has. So between about 20 centimeters a second and about 10 centimeters a second, your flowing body of water, your river, it has the capacity to move a sand grain of 1 millimeter in diameter. Once you get below 1 centimeter per second, your river has to deposit your 1 millimeter sand grain. So once your flow gets below 10 centimeters a second, it has to drop that 1 millimeter sand grain. So this is the power of the Hjulström diagram. It gives you essentially a range within which your river is capable of eroding, transporting and depositing particles of certain sizes. And that's very, very helpful to us. So if we come along and we find what we believe is a river sediment that contains lots of 1 millimeter size sand particles, well, it gives us some idea of the velocity, the flow velocity that would be required for our river to have actually moved those particles. And so it gives us some idea about how fast our river was actually going. Now, one part of the Hjulström diagram that's quite interesting is over here on the left. You'll notice that clay over here doesn't actually have essentially a range of deposition. You'll notice that whatever the velocity for deposition is, it's off the bottom of the diagram here. You can't see it. And that's because the deposition of clay is extremely difficult. Your water literally needs to come to a complete 100% stop before the clay can be deposited. The reason for that is the clay is actually held in suspension in the river water. So as long as your river water is moving, your river water has the capacity to retain the clay. It's only when your river water comes to a near 100% stop and the velocity drops to near zero that the clay can actually be deposited. So you'll notice that clays and very, very small silt particles don't actually have a velocity of deposition because it has to be really, really low. The other thing you'll notice is the ability of a river to actually erode clay and silt-sized particles actually gets worse as you move to this very, very fine material. So you would assume that the path you would take is, obviously you would need lots and lots of energy to erode very, very large material, and as the material got smaller, you would assume you would need less and less energy to erode it, which would be perfectly logical. However, once we get from very, very fine sand particles and we start going into silts and clays, you'll notice the velocity required for erosion actually begins to increase again. And the reason for that is clay and silt-sized particles have a very natural cohesion to them. They all stick together. So, I'm sure if you ever picked up a sandy sediment, you will know that, a sandy sediment has very low cohesion. It will literally run between your fingers. In contrast, a clay or a silt dominated soil, like the soil we have here in Houston, when you try and dig up something in your back garden, you will know the soil is extremely cohesive. It's very difficult to actually dig up, and it'll be sticking to your hands and your boots and your spade as you try and dig a hole or dig up whatever you're trying to remove. It's a very cohesive, very sticky material. So in order to actually erode the kind of material that contains a lot of clay and silt, you actually need to increase quite a bit of energy. You need to give quite a bit of energy in order to make that happen. So this increase in the velocity here is due to the cohesive nature of clay and silt dominated material, which is always quite interesting in my opinion. Alright, so that's the Hjulström diagram. It's just a method of trying to work out what conditions you need to erode, transport and deposit a particle of a certain diameter. So once we're actually transporting our material in a river, remember this is by water, how do we actually transport it? Well, there's actually 5 ways in which we can transport material. So the first kind of way we can transport material by river is not actually written on this slide, but it's as ions. It's completely dissolved in the water. So we discussed how when you had limestone in contact with water, the limestone would naturally break down and the calcium ions and the carbonate ions would dissolve in the water. So those were individual ions actually mixed in within the water, between the water molecules. So that's, you can't see that kind of material, it's just held within the water. Now, these other methods are going to move physical particles. So the first way we can move a physical particle is by suspension. So in order to suspend something, by its very nature, it has to be very, very light, because it's being suspended in the water. If it has any kind of real mass to it, it will fall out of the water and it will become essentially part of the bed load at the bottom of the river. So suspended particles have to be very, very light, and therefore they have to be clays and silts. So within the water itself, you will have very, very small particles held within the water. They're not dissolved in the water, they're just held within the water. And they'll be retained in the water as long as the water is moving. As long as the water has some kind of velocity, it will be able to suspend these particles within the water. So in order to deposit those particles, the water must come to a near complete stop. So that means any sediment that we find which is very, very rich in clay and silt-sized particles, well, that instantly tells us we must be dealing with some kind of environment where water has come to a near complete stop or is moving extremely slowly. So it's got to be an environment like the deep ocean, a lake, or the floodplain either side of a river, for instance. Now, larger particles, typically sands, gravels, etc., will be moved as part of the bed load. So the bed load is the material that is found on the bottom of the river. Now, in order to move material as part of the bed load, it's typically moved by one of two methods. The first method is traction. So traction is simply the force of the water hitting the particle will just push it or roll it along on the bottom of the river. The other method by which particles can be moved along as part of the bed load is through a process called saltation. And this is a bouncing or a leapfrogging action. So when the water is moving along for very, very short periods of time, it has just enough velocity to pick up our particle. So it picks it up, but it doesn't have that velocity doesn't stay for long enough. Eventually the river loses the velocity required, and so the particle has to be dropped. And so what happens is the particle gets picked up and then dropped, picked up, dropped, picked up, dropped. So the particle is literally bouncing along, leapfrogging along the riverbed. So these are the methods by which we can transport material in a river. It can be dissolved as ions, it can be suspended in the river water, or it can be part of the bed load. If it's part of the bed load, it will typically be moved by one of two methods: traction, which is rolling or pushing, or saltation, which is bouncing. Now, we've already covered this, so we're not really going to worry about it too much. But in this diagram here, it's just giving us a very crude list of environments in which you would expect to find class sizes of a certain nature. So the other thing you'll notice, by the way, here in red is that it says high energy environments and low energy environments. So once again, the larger the class size, the more energy is required to move it. So if we just look at this picture in the background here, for instance, well, what can we see? We can see as part of the river sediment on the side of the river, we have lots and lots of pretty substantial pieces of rock. Okay, those are cobbled versus running into boulder-sized pieces of rock. So obviously that requires quite a lot of energy to move them. So when we find sediments with these kind of very, very large class in them, well, there's only a very limited number of environments in which those large class can be moved. Environments like fast-flowing mountain rivers, glaciers, or landslides would be a good example of that. So as we come down, the amount of energy is decreasing. So let's think of something like a sand. Well, where would we expect to find a sand? Where would we expect to find sands in? Your normal meandering river, a beach environment, or a desert. Now that's because the energy of the transporting medium is now moderate. So a moderate transporting medium can move medium-sized particles and small particles. So it can move things like clays, silts, and sands. But the transporting medium does not have the capacity to move large stuff. So it can't move gravels, cobbles, and boulders. So we would never expect to find gravels, cobbles, and boulders in the sediment because they could never be there. So a desert sediment, for instance, would be dominated by sand because we're moving wind. We're moving the class by wind, and wind would not have the capacity to move the very, very large particles like gravel, for instance. as with the class size gets smaller, silt and clay, you can see we're moving into lower and lower energy environments. So silt, we expect to find it in environments like deltas, where a river hits the ocean or a lake, and essentially the river velocity drops very, very close to zero. It's like driving your car into a wall. Essentially, you may be driving your car at 40 miles an hour. As soon as you hit the wall, your car's coming to a complete stop. And the same happens for the river. When the river hits the ocean, it loses its velocity, and so it starts dumping its finest particles, things like silt. Clay, on the other hand, is the finest of all particles. Once again, it's suspended in the river. And in order to let clay drop out, you have to be in an extremely low energy environment. The water must be nearly still. So you've got to look at the deep ocean, a lake, or a swamp environment to have very, very clay-rich sediments. Alright, so this is another diagram we've already seen before. As you can see, it lists several environments of deposition on both the continental setting, the marine setting, and of course the transitional setting, or the intermediate setting. So, as we just touched on, there are these three broad groups of environments of deposition. There's the terrestrial or continental setting. That covers sediments deposited on land or in fresh water. So that covers things like glaciers, deserts, but it also covers sediments deposited by rivers. Then we have the transitional or intermediate settings. They are deposited in environments that are sometimes submerged or exposed. So these settings are very often tidally controlled in some way. So we're thinking of environments like beaches. And then finally you have the marine settings. Those are settings where sediments are deposited in environments that are constantly covered by salt water, by marine water. Okay, so let's look at some environments. So we're going to start off with the continental environment. So we're going to look at the environment of deposition. We're going to discuss them briefly, and we're going to think about the types of class we would expect to find in these environments, and therefore the types of sediments we would expect to find. Okay, so in the continental setting we have sediments deposited on land or in fresh water. They are dominated by stream erosion and deposition. So there's, on the continental setting, most of the sediment being moved around is moved around by water. So it's moved around by rivers. There is a small input from glacial processes, from wind and from gravity as well, but on the whole they are nowhere near as important as water. The sediments that we find in the continental setting are predominantly what we refer to as siliciclastic. They are sediments which are dominated by quartz normally. So we would expect to find plenty of quartz moving around in continental systems. I should say, siliciclastic minerals are, sediments will be dominated by quartz, but it will also contain other silicate minerals like feldspars. So here's a list of environments of deposition. So these are all continental. So the environments we're going to think about are alluvial fans, fluvial systems, glacial systems, aeolian systems, lacustrine systems, poloidal systems, and evaporites. So alluvial fans, well, we'll come on to those in a second. They're a type of desert deposit. Fluvial, river deposits. Glacial, deposited by glaciers. Aeolian, deposited by the wind, so normally desert deposits. Lacustrine, lake deposits. Poloidal, swamp deposits. Evaporites, formed by the evaporation of water. Okay, so do you know what? It's time to stop this video for now. So stop the video here, go and get yourself some water, cup of tea, cup of coffee, have a walk around, and then please come back for part 3.